Congratulations, we have made it halfway through the units, at least as far as number of units are concerned. We are done with 4 units of the 8 units we're going to cover. Some of these later ones are a little bit shorter, so we're not halfway through, we're past halfway through the semester at this point. Unit 5, we are going to start looking at systems of equations and inequalities. This first part here is looking at systems of linear equations in 2 variables. We have some objectives here that we want to go through. We want to determine if an ordered pair is a solution to a linear equation, really a linear system, not just a linear equation, but the whole system. And then we want to solve linear systems using the substitution method and the addition method. And then last, we want to identify if systems have no solution or infinitely many solutions. Some of this may feel very familiar to you, and you may feel like it comes pretty easy to you. That's okay. This is a prerequisite for some courses coming into this, show you this stuff. So that's okay. Just take it, as a nice easy break after some of the things we have covered and where we're headed. I wanted to start this section by talking about this picture and what it really tells us. You are asked to interpret the point of intersection of these 2 lines. It doesn't really matter what the equations of these lines are. What I want to know is it appears that point of intersection is when the number of miles equals 3 and the number of, or the total cost is $8. It kind of appears that ordered pair is 3, 8, right? That's not really interpreting the point of intersection, though. I mean, it is interpreting that point that is on these lines, but it is not interpreting the point of intersection. What that tells us, the fact that that is a point of intersection, means that point is on both of these lines. If that point is on both of these lines, then it means that is where these 2 cabs cost the same amount for the same number of miles. That would be our interpretation. The cabs cost, I should say, let's say both cost. Both cost $8 for a 3-mile trip. Well, we made it all the way to chapter 5 before my son interrupted any of these videos. So here he is. We can say hi one time. Say hi, Malachi.
Hi.
Hi. Okay, can Mommy get back to work?
I want Mommy.
I know you want Mommy, but I gotta get back to work, okay? You go? Okay, I'm gonna pause the video. We'll be back in a second. Okay, I'm back. Sorry about that. I could edit that out, but I probably won't because he's pretty darn cute. Okay, so we were talking about this application problem and recognizing that knowing the point of intersection is valuable because beyond that point of intersection, so beyond 3 miles, the blue cab is cheaper, right? Because the cost is lower than the yellow cab. But less than 3 miles, you would probably opt for the yellow cab. So that's the value of knowing something like that. A system of equations is 2 or more equations solved simultaneously. Any solution to the system must be a solution to all equations. Not just one. If it only works in one, it's not a solution of the system. It has to work in all of them. This ordered pair, 3, 8, works in both of these equations because it is on both lines. There's no other point that is on both of those lines, so no other point would be a solution of both equations. Let's check it out. The way we do it is we just plug it in. 2 times 3 minus negative 1, is that actually equal to 7? And the answer is yes. 6 plus 1 is 7. And let's check it in the other one. So we're checking 3, negative 1 here. Negative x plus 2 times the y value is negative 1. Is that equal to negative 5? And the answer is yes. You get negative 5 equals negative 5. That tells us 3, negative 1 is a solution to the system. Let's check negative 2 too. 2 times negative 2 minus 2, is that equal to 7? Well, no, because that's negative 4 minus 2. Negative 6 is not equal to 7. I don't even have to check it in the other one. It has to work in both, so if it doesn't work in one, we're done. That is not a solution to the system. How do we find that solution? That's fine if we are given a system and then we're given some points to check and see if they are solutions. But what we want to know is, if we're just given equations, how do you find that solution? First, I want to focus on the graphical method because it's valuable to think about the picture of what is happening. As we saw above, the solution to the system is the point of intersection. It's the only way you have a point that is on both lines. Let's take a look at this graphically. We're going to solve this graphically, and then we're going to do these same, we're going to do a few graphically, and then we're going to do these same systems using other techniques, algebraic techniques. I'm going to graph that first line, y equals negative 2x plus 4. 1, 2, 3, 4 is my y-intercept, slope of negative 2. So I'm going to go down 2 to the right 1, down 2 to the right 1, down 2 to the right 1. If you need to refresh on how to graph lines, go back to Unit 2. I think it was Unit 2, maybe Unit 3. Unit 3 maybe. And refresh on graphing lines. Oh, shoot. So there's my line, the first one, y equals negative 2x plus 4. Now let me pick another color and we'll graph the other one. Y equals 3x plus 9. 4, 5, 6, 7, 8, 9 is here. And then I'm going to go down 3 and left 1. Down 3 and left 1. Down 3 and left 1.
Mommy.
And we're back. We did so well while he was at the zoo all day today, and now we're back. Okay, I'm back. I have to do a little bit of editing to figure this out, so I'm trying to jump back in where we were. Normally I would just restart the video, but I have done so many videos today, I am exhausted. So I'm just going to try to edit what I can and make this work. We saw graphing these two lines that y equals negative 2x plus 4 gave us the black line, and then I think we are graphing the red line here, and that is y equals 3x plus 9. It appears that these two lines intersect right there at negative 1, 2, 3, 4, 5, 6. And that seems to be the case from the slope. And I'm not just guessing here. If your y-intercept is 9 and you go down 3 into the left 1, that does take you to that point, negative 1, 6. Same thing with this point, y-intercept of 4. If you go up 2 into the left 1, it takes you to negative 1, 6. So we can see that this is actually the point of intersection there. So that is the solution. The solution is x equals negative 1, y equals 6. You can always check your solution that you come up with in the original equation, right? You can start with that y equals -2 times -1 plus 4 with a question mark over it. Is that really equal? Yes, it is. And then you have to check it in the other one, right? 6 equals 3 times -1 plus 9. Is that really true? Plugging it in the second equation, 6 equals 6. Yes, it is. So it does work. It's always a good idea to check that to make sure it does work. We're going to do another one here, mostly because I want to show you something specific. In this case, we really have two options. We can plot the x and y intercepts if we wanted, or we can put it in slope-intercept form. Let's go with that. 3x minus 3y equals 1. Subtract 3x from both sides and divide by -3. I get y equals x minus 1/3. Okay. Let's, just because this y-intercept is a fraction, I'm going to go 1, 2, 3. So I'm going to make my scale 1/3 here. Each of these marks is going to be 1/3. So we have that. When I go to graph that, let me grab a different color here. I'm going to graph that line in red. Oops. If this is -1, then -1/3 will be here is my y-intercept. Now slope of 1, technically I could go up 1, which would take me to this 2/3, and over 1. But realistically, going up 1/3 and over 1/3 works too. So each of these marks, because the scale is equal, each of those marks is going to be equal, which is all you need if your slope is 1. You need the x and the y to be equal, right? The rise and the run. Okay, so that is the first line, the 3x minus 3y equals 1. Let's go ahead and go to the second line. 6x minus 6y equals 2. When I solve that for y, I get -6y equals -6x plus 2. Divide by -6 gives me x minus 1/3. That's the same line. Y-intercept of 1/3, graph it, it's going to be right on top of that line. So now the question becomes, what is the solution to this system of equations? And the answer to that is, where do they intersect? All points on the line 3x minus 3y equals 1 are solutions to this. Or you could write 6x minus 6y equals 2 in there. They're the same line. It doesn't matter. So every point. That means this has infinitely many solutions. What I don't want you to do is say all real numbers are solutions, because that's not true. This point out here, not a solution, right? It is just the ones that are on the line. So that's that scenario. Those are the same line, and that was the result we got. So let's make a little note here. Same line. One more example. Let's look at this guy. 2x minus y equals 4. Let's write that as y equals 2x minus 4. And then the second one here, this guy, when I rewrite it, what is going on here? There we go. When I rewrite that, I get 2y equals 4x plus 6. When I divide by 2, I get 2x plus 3. So let's graph these two lines. This one's the first one. That's the second one. y equals 2x minus 4. Use y-intercept is -4. Slope is 2. Rise 2, run 1. Rise 2, run 1. I'm just going to go till I run out of space here. That's how I get my best picture. Okay. Try and zoom in a little bit so I have better space here. Zoom out. Okay, the other one, so that's y equals 2x minus 4, that y-intercept of -4. The other one is y equals 2x plus 3. So there's my plus 3. Rise 2, run 1, up 2 over 1, up 2 over 1, down 2, over to the left 1, and so on. Okay. So this is my picture here. I'm looking for points of intersection. Well, they don't cross on this picture. That doesn't mean they won't cross outside of this picture, right? They could be getting closer and closer and closer together, just really really close, really far away. They're just getting close together really slowly. But we know that they're not actually doing that because they have the same slope. These are parallel lines. So this system of equations has no solution. There's no point that these intersect. There's no point they have in common. So that's our graphical situation. We can have them intersect at one spot, we can have them intersect at an infinite number of places, or we can have them intersect at no place. And we know the point of intersection is the solution. Let's take a look at how these can be found algebraically. We have two methods for that. One is called the substitution method. Here's what we do. We choose one equation and isolate one of the variables, then substitute that into the other equation. Hopefully that'll be pretty clear once we see that. Here, we already have y isolated, right? So I can take what y is equal to. Here I have y equals 3x plus 9. In the first equation, y is equal to -2x plus 4. So I substitute it right in there. The only variable left is x, so we solve for it. 5x is equal to -5, so x equals -1. And then pick either equation, it doesn't matter which one, and put the -1 in it. I just picked the second one because it didn't already have a negative in it, but it doesn't matter. You get y equals 6. -1, 6. Same thing we got when we looked at them graphically. That's the exact same system that we saw in our first graphing example. This is our second example that we saw graphing. We know that that had an infinite number of solutions. Let's see if we try to isolate, oh wait, hold on. We had already done the work to show us that this is y equals x minus 1/3. We're going to take that x minus 1/3 and put it in place here. You could solve for either x or y in either equation. I just chose that because we had already done it above, but it doesn't matter in this case. 6x minus 6x plus 2 equals 2. That simplifies and gives us 2 equals 2. Sometimes at this point students will say, oh, x equals 2 and y equals 2 because I have 2 equals 2. No, there's nothing there that says x equals 2 or y equals 2. All this tells us is that we have a true statement. When you have a true statement like that, it means you don't have any contradictions, and that's where we get that infinitely many solutions. And that tells us they are the same line. okay? Which is what we saw above when we graphed it. One other method we can use is the addition or elimination method. Our goal here is to eliminate one of the variables by adding the two equations. That means that I want one of the variables to have opposite coefficients. So if I have 2x in one equation, I want negative 2x in the other equation. Okay? In this case, this example, this first example, I have y equals negative 2x plus 4, y equals 3x plus 9. It's usually easiest if you write both equations in that form. 2x plus y equals 4, negative 3x plus y equals 9. Now our goal here is to have opposite coefficients on one of the variables. We are going to do that by multiplying this equation by negative 1. That'll give me 3x minus y equals negative 9. I'm going to bring this equation down, 2x plus y equals 4. I didn't change anything there, I just brought it down. I'm going to add these now. That gives me 5x plus 0, negative y plus y is 0, equals negative 5. I have eliminated the y. X equals negative 1, and then substitute into one of the other equations, one of the equations to get the 6. So we get that negative 1, 6. That's the addition or elimination method. I really like it in particular when the equations are already written in ax plus by equals c form. They don't technically have to be in that form, but I tend to see less mistakes when they are. Let's take a look at this one. This is a new system. We haven't seen it yet. This one that we just did, we saw in using all three methods, graphing, substitution, and this addition method. We want opposite coefficients on one of our variables. We just want to choose wisely here. This 2x minus 3y equals 1, 3x minus 2y equals 4. I'm thinking I probably want 6 on x and negative 6 on the other x. What do you think? If we multiply the top equation by 3, that will give me 6x minus 9y equals 3. If I multiply the bottom equation by negative 2, that gives me negative 6x plus 4y equals negative 8. Then I add those together, and the 6x minus 6x gives me 0. Negative 5y equals negative 5. That tells me y equals 1. And I have to find the x also. So I got to go back to one of my equations. I don't care which one you choose. 2x minus 3 times 1 equals 1. 2x minus 3 equals 1. 2x equals 4. That tells me x equals 2. So my ordered pair solution is 2, 1. If you're writing it in with variable notation, x equals 2, y equals 1. Let's do another one. This one is kind of nice in that it already has one of the coefficients on x positive and the other one negative. I'm going to multiply by 2 here so that I can get 4x minus 2y equals 8, and then add it with this equation here. The x's eliminate. Oh, wait a minute. The y's also eliminate. And I get 0 equals 14. Wait. Never in my life has 0 equaled 14. That's a false statement. That's what we call a contradiction. And it means we have no solution. Okay? Let's do an application of this so we can just kind of see what we need to where we might use something like this. These are linear. All these systems are linear, so that's where we're at here. Suppose a theater group sells 500 total tickets. The cost was $15 at the door and $10 in advance. If they made $6,705 total, how many of each type did they sell? Well, our two types are door tickets and advanced tickets. And it's how many of each, right? So I'm going to let X be the number of door tickets sold. And I'm going to let Y be the number of advanced tickets sold. Being very clear about what my variables are here. Those are the two things I want to know, so that's why I'm calling them my two variables. Suppose a theater group sells 500 total tickets. That tells me that X plus Y equals 500, right? Sum of the two types of tickets, numbers of the two types of tickets, will be 500. The cost was $15 at the door and $10 in advance. It made $6,705 total. That means 15x will be the amount of money they bring in from door tickets, and 10y will be the amount of money they bring in from advanced tickets. The sum of those two is going to be that 6,705. That's my system of equations. You have two options here for how you approach this. If you want to use the substitution method, I would probably recommend taking the first equation and solving it for either X or Y. It's just the simplest to get X or Y alone. The second equation is going to be a little more complicated, just bigger numbers to deal with. Not a huge deal, but you could do it, and it might result in some fractions, which I would not recommend. Or your other option, which I would probably use, is to take the first equation and multiply it by -10. Because that will give me -10x minus 10y equals -5,000. Why did I do that? Because when I add these two, it's going to eliminate the y and leave me 5x equals 1,705. And now I need to divide by 5 on both sides. 1,705 divided by 5 gives me 341. 341 is X, so that's the number of door tickets. And then I would use that first equation, X plus Y is 500. 341 plus Y is 500. So Y is 159 advance tickets. The sum of them is 500. Did we answer our question? I always like to make sure. How many of each type did they sell? Yes, we did answer the question. So there was an example of where we had to write the equations based on an application and then decide which method was better. I personally, in this case, like the addition or elimination method. But it would be very easy to solve for X or Y in the first equation and substitute into the second equation. So whatever your preference is fine.